potential energy of system of charges. So now we have just seen that the expression is k q1 q2 by r. Now we will see what if the charges are like charges and what if the charges are unlike charges. So like charges in the sense both will be positively charged or both are negative charged. Unlike charges means both are oppositely charged. So in case of like charges, we say potential energy of the system is positive. Why? Because you please see Q1 and Q2. So this is also positive, this is also positive. So the total result is positive, plus into plus plus. Similarly, if both are negative, then it is minus into minus, again plus. So for the system of like charges, potential energy is positive. If it is unlike charges, then it will be plus into minus minus. So for unlike charges, the potential energy of the system will be negative. And you also know very well, if there are like charges, that is positive and positive or negative and negative, then they will repel each other. If that means positive, and if we take positive and positive system, positive will repel the positive. So there will be a repulsion. If we are taking negative and negative, again negative will repel negative charge. So there is net repulsion. If we take unlike charges 1 plus and 1 minus, then there will be net attraction, because for positive charge will attract the negative charge, and in that case we have seen potential energy of the system is negative. So I have shown it in the graph. So this is the graph between potential energy and the distance. Okay, this distance between the charges. So we know use k q1 q2 by r. Okay, so it is inversely proportional to r. So the general graph will be in this way. Okay, now we have shown it for like charges and unlike charges. We have seen for like charges q1 and q2 will be greater than 0. Why? Because positive into positive or negative into negative, that will be resulting in positive. Okay, so that will be greater than 0. Similarly, if we take unlike charges, q and q2 will be less than 0, because it is negative value, plus into minus or minus into plus. So both are negative value. So it is lesser than 0. Okay, so now, so please see for like charges, it is positive. That is potential energy of the system is positive. So we have represented in the this side. Okay, this is potential energy axis, and above this it is positive axis, and below this it is negative axis. So for like charges, we have shown it in the positive axis. Okay, for unlike charges, potential energy of the system is negative. So we have shown it in the negative axis. Now, yes, we will learn one more thing, net attraction or net repulsion force between the charges. So, this is a general formula, F is equals to minus du by dr. So, this is how force, we find force when there is a potential energy. Okay, F is equals to minus du by dr. Please remember this expression. Okay. For a system, potential energy is minimum in condition of stable equilibrium. So if we take any system, then for the system to be in equilibrium, the potential energy should be minimum. Okay, so this is a general case. Whenever we want the system to be in stable equilibrium, then the potential energy should be minimum. Okay, only then it will be in stable equilibrium. Please remember that point. It is important. Now we will see potential energy of this system, where it comprises of three charges q1, q2 and q3, and they are separated by a distance. Q1 and q2 are separated by a distance r12, and q2 and q3 are separated by a distance r23. Q1 and q3 are separated by a distance r13. Okay, so this is the case. So for two charge system, we just had one combination, that is q1 and q2. Now we have how many combinations? Q1 and q2, q1 and q3, and q3 and q2. So there are three combinations here. Okay, so if we take q1, it is in combined with q2 and q3. Similarly, if you take q2, already we have seen with q2, so it is now it is with q3. So Q3 we have already seen one combination with Q1 and one combination with Q2. So this is how we used to write the potential energy of this system. So U equals to K, that is 1 by 4 pi epsilon naught, Q1 into minus Q2. So this charge is minus Q2. Okay, this is a negative charge, so we have written minus Q2 by R12, the distance between those two charges. Next combination we have to take is any two. Okay, we are taking q2 and q3, so it is minus q2 and q3 by r23 plus q1 q3 by r13. So that is simple. So just we are simplifying it. We have just taken the minus here, we have just taken this minus here, so we have just given this. So this is the electric potential energy of this system. Okay, equipotential surface. Any surface over which the electric potential is same everywhere is called equipotential surface. So if we take a surface where the electric potential is same, okay, in that surface if electric potential is same, then it is called equipotential surface. Let us consider an example. So here we have a positive charge plus q, and what is the electric potential because of this positive charge plus q at a distance r? It is kq by r. Okay, and if we take this point which is also same distance from the r, so from the q, so this point is at a distance r from this charge q. So the electric potential at this point, let us suppose a, it is kq by small r. Suppose this point we have taken it as b, which is also at the same distance from the charge r. Okay, then what will be the electric potential at the point b? Then it is also kq by r only. So what we can say, these two places, these two points have same potential. So if similarly if you consider this as a sphere, okay, this sphere, okay, this, like if you consider this as a sphere, then the surface of the sphere will be at a distance r, small r, from the charge q. So everywhere on the sphere you can see the same potential, that is kq by small r only. So the entire sphere can be taken as a equipotential surface because everywhere on the surface of the sphere with radius r, okay, the electric potential is same. So we can say it is a equipotential surface. So this is nothing but electric field lines. We know for positive charge plus q, the electric field lines are radially outward, and it is in the like a sphere. It is spherically distributed around that charge. Now these are the equipotential surfaces. Imagine it is a sphere. Okay, just I am showing in the two-dimensional way, but you have to imagine it in a three-dimensional way like a sphere. Okay. Now if suppose we take in another case, if this is the electric field lines or lines of force, okay, then this surface, so please imagine this is perpendicular to it. Okay, this surface is actually perpendicular to the field. Okay, so this, at this point the electric potential is same, so this can be taken as a equipotential surface. Similarly this can be taken as an equipotential surface. Let us learn some points about the equipotential surface. No work is done in moving a charge between any 2 points on the equipotential surface. So actually we know work done. What is work done equals to Q into V final minus V initial. So if we move a charge in the equipotential surface, then we know on the equipotential surface the potential is same over everywhere. So V final will also be the same value as that of V initial. So W will be equals to Q into V final minus V final, that is 0 only. So the work done will be 0, okay, because there is no change in potential. So work done on the moving charge in equipotential surface is 0. Please note that point. Electric field, hence lines of force are at right angles to the equipotential surface. So here you see this is the electric lines of force and this is the surface. So this surface and this electric lines of force will be perpendicular to each other, that is the angle made by the surface with the electric field is 90 degree. In family of equipotential surface, the surfaces are closer to each other where electric field lines is stronger, and farther apart where the electric field is weaker. So if electric field is stronger, then we can see the surfaces are closer to each other. Okay, if electric field is weaker, then the surfaces will be, that is equipotential surfaces will be farther apart from each other. Okay, we have just shown it. E is equals to, actually we know electric field is inversely proportional to the distance, so that is what they have told. If E is stronger, then the distance will be lesser. Okay, as they are inversely proportional, if a distance is more then electric field strength is less. So like that we can get it. No two equipotential surface intersect each other. So no two equipotential surface can intersect each other. Okay, that is also one more point. So please note it. Potential due to an electric dipole. Previously we have seen the potential due to a point charge. The formula is Kp by R. So now we are going to see the potential due to electric dipole. So here we have to take the inclination of R. Okay, so what is R? So this is R. So if suppose this is the dipole and if this is the point where we have to find the electric potential, then this is the distance, that is from the center to the point P, the distance is R. Okay, and the angle made by this R with this line, okay, with the dipole moment is theta. Okay, now we are going to consider that angle also. Okay, please note that point. So the general formula is V equals to Kp cos theta by R square. So now we are seeing only the results because it is enough for us. So V equals to Kp cos theta by R square volts. So this is the general formula. Now we will see about equatorial and axial line. So first we will see about the axis. So what is axis? This line. This is the axis and this is the axial line. So in axial line we have a point P which is at a distance r from the center of the dipole. Now this is minus q, this is plus q, and they are separated by a distance 2l. So here P is nothing but 2 into Q into L. So here P value is 2QL and we are not separately writing it. Just please remember that because it is a dipole moment. Now here we know it is Kp cos theta by R square. So this is the direction of R and this is the direction of dipole moment. So the angle made between them is 0. So it is Kp cos 0 by R square. What is it? Cos 0 is 1. It is just Kp by R square. That is 1 by 4 pi epsilon naught P by R square. So this is the electric potential at the axial line. Okay, because of a dipole. Now we will see about the equatorial line. So when we take equatorial line, so it is like this, minus q plus q, and it is separated by a distance 2l and the point P is at a distance r from the center of the dipole. Now we have Kp cos 90 by r square and cos 90 is 0. So the potential due to electric dipole in the equatorial line, wherever it may be on the equatorial line, the potential due to electric dipole is 0. So please note this point. So there is only yes, at the equatorial point there is zero potential because of the dipole moment. So please remember that. Potential due to point charge and potential due to dipole, just we are seeing the differences. So potential due to point charge is nothing but kq by r, so it is dependent on r. Potential due to dipole is dependent on both r and the inclination of r. Okay, we have just now seen the theta, it is dependent on the theta also. Okay, than r, it is also dependent on theta. So there we have seen it is kq by r. So if it is kq by r, then it is inversely proportional to r. So here what is the formula? Kp cos theta by r square. So V is inversely proportional to r square. Okay, so here it is inversely proportional to r, here it is inversely proportional to r square. So yes, here the formula is shown. Okay.